These are the answers to the atomic structure and nuclear chemistry practice test. In the video description area, there is a link to the packet that accompanies this video. For questions 1 through 7, the answers are either John Dalton, Democritus, Antoine Lavoisier, Ernest Rutherford, or J.J. Thomson. So we'll go from earliest to latest in terms of the timeline, starting with Democritus. So the Greek word atomos means uncuttable or indivisible. Therefore, Democritus, choice B, is the correct answer to number 3. He was a philosopher who believed in the existence of indivisible particles of matter. In his language, the word atomos means uncuttable. Next, let's take a look at Antoine Lavoisier. He discovered the law of conservation of matter, which states that matter is neither created nor destroyed in chemical and physical processes. So Lavoisier, choice C, is the correct answer to number 6. His attention to detail helped him to discover the law of conservation of mass, or matter, in the 18th century. His experiments showed that in a chemical reaction, matter is neither created nor destroyed. So the next person in our timeline is John Dalton. And in 1803, John Dalton published an atomic theory, and some of the postulates are the following. All matter is composed of tiny particles called atoms. He also said atoms of one element combine with atoms of another element to form a compound. So John Dalton, choice A, is the correct answer to number 2. In his atomic theory, published in 1803, he stated that matter is composed of atoms. He also stated that atoms of different elements combine together to form compounds. The next person in our atomic theory timeline is J.J. Thomson. Thomson did work with cathode ray tubes. Thomson discovered that these cathode rays contain negatively charged particles because the cathode ray is attracted toward a positively charged electric plate. These negatively charged particles, which were eventually called electrons, are so much lighter than the positively charged material that the plum pudding model of the atom shows that the entire mass of the atom is a big ball of positive charge, and then embedded in this plum pudding model, embedded in the positive charge, are these negatively charged electrons. So the answer to number 1 and number 5 is J.J. Thomson, which is choice E. He did cathode ray tube experiments, which helped him to discover electrons, and his plum pudding model of the atom is based on the fact that the positive material in an atom is much heavier than the negative particles. And the last person in our atomic theory timeline is Ernest Rutherford. Ernest Rutherford is famous for his alpha scattering experiment, where a narrow beam of alpha particles was directed at a thin piece of gold foil. Now, the alpha particles, most of them, passed straight through the gold foil, but because a few of the alpha particles were deflected at large angles, then Rutherford concluded that the majority of an atom's mass and positive charge is contained in a tiny nucleus. So correct answer to number 4 and number 7 is choice D, Rutherford. Number 4, in his famous alpha scattering experiment, a stream of alpha particles was directed at a thin piece of gold foil. A small percentage of the alpha particles were deflected at large angles. And number 7, his experiments produced a surprising result, which showed that the plum pudding model of the atom is incorrect. In his atomic model, an atom contains a tiny, positively charged nucleus. In the next part of the practice test, these are questions 8 through 16, you have to fill in each blank with one of the following words: protons, electrons, or neutrons. Let's take a look at number 8. So we are given a neutral atom of lithium-7, and the atomic number of lithium is 3. That means that lithium contains 3 protons. The fact that the mass number is 7, and the mass number is the sum of the protons and neutrons added together, we have 3 protons, therefore we have 4 neutrons. There is no charge on this particular atom, so because it's neutral, the number of protons and electrons is the same, so 3 minus 3 is 0. Therefore, this particular answer is protons and electrons. Now, moving on to number 9. If a neutral atom of oxygen gains 2 blank, it becomes an oxide anion. So a cation is a positive ion. An anion is a negative ion. And you can remember that the word cation sounds like cat, so a cation is an ion with a positive charge. That helps you remember that. So what happens in terms of how does an atom become an ion is if an atom loses electrons, it becomes a positive ion, which is known as a cation. And if, on the other hand, an atom gains electrons, it becomes a negative ion, which is known as an anion. So correct answer for number 9, if a neutral atom of oxygen gains 2 electrons, it becomes an oxide anion. All right, moving on to number 10. The nucleus of boron 10 contains 5 of this and 5 of that. So the atomic number of boron is 5. That's 5 protons. The mass of this particular isotope is 10, and that's the sum of the protons and neutrons. Therefore, there are 5 protons and 5 neutrons. And this is a neutral atom, so there is no charge. Therefore, it contains 5 protons and 5 electrons. So the key word in this sentence to help you answer the question is the word nucleus. So protons and neutrons are located in the nucleus, but the electrons are located in the cloud outside the nucleus. So the correct answer to number 10 is protons and neutrons. All right, moving on to number 11. A neutral atom of carbon-14 has 2 more blank than a neutral atom of carbon-12. So there's carbon with either a mass of 14 or 12. The mass number is the sum of the protons and neutrons. Carbon has atomic number 6. That's 6 protons. So therefore, if it's 14 for the mass, that would be 6 protons and 8 neutrons. If it's 12 for the mass, that would be 6 protons and 6 neutrons. So the only difference is the number of neutrons. Different isotopes of the same element have the same number of protons, but a different number of neutrons. So number 11, correct answer is neutrons. Number 12, blank are assigned a mass number of 0 because their mass is so much smaller than the mass of the other subatomic particles. So again, J.J. Thomson had discovered that these electrons are so much lighter than the mass of the positively charged particles, which again eventually became discovered as protons. And neutrons and protons are pretty similar in their mass. So correct answer for number 12 is electrons, which weigh so much less than either the protons or the neutrons. All right, let's take a look at number 13. It says a neutral atom of cobalt-60 contains the same number of blank as the cobalt-59 ion, which has a 2+ charge. So on the periodic table, we see that cobalt has atomic number 27. So one of the symbols is cobalt-60. It does not have a charge. And the other symbol is cobalt-59, and it has a 2+ charge. So we'll start with protons. The symbol on the left has 27 protons. The symbol on the right also has 27 protons. For electrons, we have to consider the charge. And if the charge is 0, if it's a neutral atom, then the protons and electrons are equal to each other. So on the left, we have 27 electrons, which matches the number of protons. And on the right, with a 2+ charge, that means that we have lost 2 electrons. So the charge is equal to protons minus electrons. That would be +2 charge, 27 protons, 25 electrons. And now for the neutrons, mass number is equal to protons plus neutrons. So 27 plus what number equals 60? And that number is 33. So 27 protons and 33 neutrons equals 60. But on the other particle, that would be 59. So it's going to have 32 neutrons because 27 plus 32 is 59. Hopefully you can see why the correct answer to number 13 is protons. All right, let's move on to number 14. A neutral atom of beryllium-9 contains the same number of blank as a neutral atom of boron-10. So beryllium is Be with atomic number 4, and boron is B with atomic number 5. If the mass number is the sum of the protons and neutrons, then for beryllium, that would be 4 plus what number is 9? That's going to be 5 neutrons. 4 plus 5 is 9. And then for boron 10, again, mass number is the sum of the protons and neutrons. 5 plus 5 is 10. So we can see that each of these samples has the same number of neutrons. So number 14 is neutrons. All right, moving on to number 15. The sodium-23 ion, which has a +1 charge, contains the same number of blank as the fluorine-19 ion, which has a minus charge. So we'll start with sodium, which has atomic number 11, fluorine, which has atomic number 9, protons, electrons, and neutrons. Let's go ahead and consider all 3 particles for each of these substances. All right, so 11 protons for sodium, 9 protons for fluorine. The mass number is the sum of the protons and neutrons, so it's going to be 11 plus what number is 23, and that would be 12 neutrons, so 11 plus 12 is 23. And then for the fluorine isotope, it's going to be 9 plus what number is 19, that would be 10 neutrons. Now for electrons, charge equals protons minus electrons. If we have a +1 charge, that means it lost 1 electron. So 11 minus 10 is 1. The sodium ion with a +1 charge has 10 electrons. If we have a negative charge, that means we've gained 1 electron. If the charge is -1, that would be 9 minus 10. Therefore, each of these ions contains 10 electrons. So electrons is the answer to number 15. And now number 16, it says an alpha particle contains or consists of 2 blank and 2 blank. So when you learned about nuclear chemistry, you learned about alpha decay and beta decay. An alpha particle consists of 2 protons and 2 neutrons. So the correct answer to number 16 is protons and neutrons. All right, let's take a look at question 17. Which of the following statements was not included in the atomic theory published in 1803 by a certain Englishman? So we're talking about John Dalton's atomic theory. John Dalton said that all matter is composed of tiny particles called atoms. He also said that all atoms of a given element are exactly the same. So therefore, the answer cannot be choice A. Did he say that atoms are neither created nor destroyed in chemical reactions? Yes. So therefore, it's not choice B. And did he say that atoms contain a tiny center of positive charge called the nucleus? No, but he did say that atoms of one element can combine with atoms of another element to form a compound. So the idea of a nucleus was not known at the time of John Dalton. So the correct answer to number 17 is choice C. All right, let's take a look at question 18. Which of the following statements concerning a cathode ray is true? You may recall from seeing this demonstration in class, or maybe watching a video, that a cathode ray can be deflected by a magnetic field. So therefore, choice B, the path of a cathode ray cannot be affected by a magnetic field. That is incorrect. When we learned about cathode rays, J.J. Thomson showed that a cathode ray is attracted toward a positively charged plate, so that's why it contains negatively charged particles. Therefore, choice A, a cathode ray is attracted toward a negatively charged plate. That is incorrect. So now the correct answer is either C or D. So choice C says a cathode ray is composed of tiny particles whose mass is much less than the mass of protons. So that's consistent with the plum pudding model of the atom, in which the positively charged particles are much, much heavier than the negatively charged particles. And as far as choice D, about using it in the famous Goldfull experiment, in fact, no. Rutherford used alpha particles, not cathode rays, to do his famous Goldfull experiment. So the correct answer to number 18 is C. A cathode ray is composed of tiny particles whose mass is much less than the mass of protons. All right, moving on to question 19. We have 4 symbols. In which of the following are the number of protons the same as the number of electrons? So when considering protons and electrons, it has to do with the charge. If the number of protons is the same as the number of electrons, then it has a charge of 0. In other words, it's neutral. So the only particle that's going to have the same number of protons and electrons is an atom that does not have a charge. So the correct answer to number 19 is D, because it does not have either a positive or a negative charge. It is a neutral atom. All right, this is question 20. In which of the following are the number of protons the same as the number of neutrons? So let's look on the periodic table and find each of these four elements so we can determine the atomic number, the number of protons. So for potassium, that's 19, that's K. For carbon, that's 6, that's C. For sulfur, that's S, that's 16. And for germanium, Ge, that's 32. So now that we know the number of protons, the mass number is the sum of the protons and neutrons added together. So for choice A, potassium 40, that would be 19 plus 21 is 40. So they don't have the same number of protons and neutrons, so we can rule out choice A. For choice B, carbon 14, that would be 14 is equal to 6 plus 8. 6 protons, 8 neutrons. They're not equal, so we can rule out choice B. And then moving on to choice D, germanium, 32 protons, and then the mass number is 66. That would be 32 plus 34 neutrons. So again, protons and neutrons are not equal. So the correct answer is choice C, and here is why. We have 16 protons plus 16 neutrons for a mass of 32. All right, let's move on to number 21. In which of the following are the number of electrons the same as the number of neutrons? Let's go ahead and make a table for each of these four particles: protons, electrons, and neutrons. Let's find them on the periodic table. So we have beryllium, Be, oxygen, O, silicon, Si, and chlorine, Cl. So the atomic number, the number of protons, would be 4 for choice A, beryllium, 8 for choice B, oxygen, 14 for choice C, silicon, and 17 for choice D, chlorine. Now, let's go back to choice A. The charge, which in this case is +1, is the difference between protons and electrons. So we have 4 protons, but since we have a +1 charge, that means we must have lost 1 electron. So 4 protons and 3 electrons would give us a charge of +1. Now for the mass, that would be 9, and that's equal to the sum of the protons and neutrons added together. So 4 plus what number is 9? That's 4 protons and 5 neutrons. All right, moving on to choice C. For the charge, it would be 4 plus. So if you have a +4 charge, that means you lost 4 electrons. So 14 protons and 10 electrons would give you a charge of +4. And the mass is 28. So 14 plus 14 is 28. That's 14 protons and 14 neutrons. And then moving on to choice D, the charge, well, there is no charge, it's 0. So we must have the same number of protons and electrons. That's 17 protons, 17 electrons. The mass is 35. So 17 plus what number is 35? That would be 18 neutrons, 17 protons and 18 neutrons. Now let's go back to choice B. The charge is -2. That means that we gained 2 electrons. So 8 protons and 10 electrons would give you a charge of -2. And the mass is 18. So 8 plus what number is 18? That would be 8 protons and 10 neutrons. So looking at the 4 choices, in which of the following are the number of electrons the same as the number of neutrons? The correct answer is choice B. All right, let's take a look at number 22. Which of the following pairs represent 2 different isotopes of the same element? Well, If it's the same element, it cannot be choice C because that's sulfur and phosphorus. Those have different elemental symbols. So the answer is either A or B because we're looking at the same symbol and therefore the same element. But the definition of isotopes is the following. Two different isotopes of the same element would be the same element with different mass numbers. Same number of protons, but different number of neutrons. Correct answer is choice B. That's carbon-12 and carbon-14. Same element, but different mass. The reason why it's not choice A is because they both have a mass of 40. One of them is an ion, and the other is an atom. All right, correct answer for 22 is B. Let's take a look at number 23. Which of the following lists the correct number of subatomic particles for a neutral atom of potassium-40? Protons, electrons, and neutrons. This is potassium with atomic number 19, so 19 protons. The mass number is the protons plus the neutrons, so 19 plus what number is 40? 19 plus 21 is 40, that's 21 neutrons. And there is no charge, so therefore if the charge is 0, protons, electrons are equal, so 19 protons and 19 electrons. So 19 protons, 19 electrons, and 21 neutrons. Correct answer for number 23 is C. All right, this is question 24. Which of the following is the correct symbol for a particle that contains 14 neutrons, 13 protons, and 13 electrons? So since the atomic number, the number of protons, tells us the symbol of the element, let's go look on the periodic table for which element has atomic number 13. So 13 protons is aluminum, therefore we can eliminate choice D, which is the symbol for silicon. Now, 13 protons and 13 electrons, that means that there is no overall charge because the positive and the negative balance each other out. So the correct answer is C. It's the only choice that has a charge of 0. All right, question 25. Which of the following statements best describes the difference between cobalt-59 and cobalt-60? Cobalt has an average mass of 58.93. Choice A says that cobalt-60 has a higher natural abundance than cobalt-59. But since the average atomic mass of cobalt is 58.93, and that value is close to the number 59, then there's no reason to assume that cobalt-60, which is heavier than that, would be more abundant. Most likely, cobalt-59 is the most abundant isotope because 58.93 is close to 59. So now we come down to that definition of isotopes. Isotopes would be same element but different mass numbers. Same number of protons but different number of neutrons. So the correct answer is D. Cobalt-60 has one more neutron than cobalt-59. That's why it's heavier. All right, question 26. Which of the substances listed below is an ion that has a charge of positive 2? Focusing on protons and electrons, let's look at those two columns. If you have a charge of positive 2, then you have more protons than electrons. So the correct answer is choice D, since 24 protons minus 22 electrons would give us a charge of positive 2. All right, this is number 27. What happens when a sulfur atom becomes a sulfide ion with a charge of negative 2? So we're going to focus on the electrons here because if sulfur becomes sulfide, it's still the same element. The identity of the atom is not changing. So because it's still sulfur, the number of protons are not changing. What is changing is the charge. And if you go from 0 to negative 2, that's because you would have gained 2 electrons. So 16 protons for sulfur, 18 electrons would give you a charge of negative 2. So the sulfur atom gains 2 electrons. Choice B is the correct answer. Okay, this is question 28. Which of these isotopes of strontium should have the highest natural abundance? We have isotopes with mass numbers of 86, 87, 88, and 89. Now, if we look on the periodic table, strontium has an average atomic mass of 87.62. So this value, 87.62, is closer to the number 88 than any of the other numbers listed in this question. So the correct answer is going to be the isotope whose natural abundance would be highest and is also closest to the average, and that works out to be 88. So the correct answer is C, and it turns out that if I give you the data, you can see that approximately 82.6% of all the strontium is actually isotope 88. That's consistent with the fact that 88 is close to 87.62. All right, moving on to question 29. If you take away one neutron from a neutral atom of cesium-133, what would be created as a result of this change? So we are not going to produce a new element, but we are going to produce the same element with a different mass. So same element, different mass numbers. We go from cesium-133 to cesium-132. The correct answer is choice B. All right, question 30. Which of the following statements concerning aluminum-28 is true? Well, let's go find aluminum on the periodic table. The average atomic mass of aluminum is actually around 27. It's 26.98. So since this value is close to 27, there is no reason to assume that aluminum-28, which is heavier than 27, would be more abundant in nature than aluminum-27. So most likely the answer is not A. Let's take a look at choice B. Aluminum-28 has one more proton than aluminum-27? No, particles that have different number of protons would have different elemental symbols because they would be different elements. So it's not choice B. Now, if in terms of beta decay, is it going to produce magnesium-28 or silicon-28? Let's review beta decay and see what happens. In beta decay, the mass number of the radioisotope is unchanged, and the atomic number increases by 1 unit. So we still have a mass of 28, but we go from 13 to 14. And so what element has atomic number 14? And that is silicon. So when aluminum-28 undergoes beta decay, it produces silicon-28. Correct answer is D. All right, question 31. An ion of scandium, Sc, has a charge of 3+. This ion contains the same number of electrons as which of the following? So scandium has 21 protons, and the charge is equal to the protons minus the electrons. So it must have lost 3 electrons if it forms a positive 3 charge. So it has 21 protons and 18 electrons. Now let's consider each of these 4 choices and see which one has 18 electrons. Starting with choice A, chromium has 24 protons, and there is no charge on this particular atom, so it must have 24 protons and 24 electrons. So correct answer is not A. Titanium, in this example, it has 22 protons, has a -4 charge, so if it has a -4 charge, it must have gained 4 electrons. So 22 protons and 26 electrons. The answer is not choice B. All right, next up is silicon, which has 14 protons. And if it has a 4+ charge, that means it must have lost 4 electrons. So 14 protons and 10 electrons would give you a charge of +4. 10 electrons, the correct answer is not choice C. Now, why is it choice D? Well, we have chlorine, which normally has 17 protons and 17 electrons. But if it has a -1 charge, it must have gained 1 electron. So 17 protons and 18 electrons would give you a charge of -1. So again, correct answer is choice D with 18 electrons. All right, moving on to question 32. Chlorine exists naturally as 2 different isotopes, chlorine-35 and chlorine-37. Which of the following is most likely to represent the natural abundance of these two isotopes? So 35 and 37. The average mass of chlorine on the periodic table is 35.45. So as we can see, the abundance of chlorine 35 should be greater than the abundance of chlorine 37 because the average atomic mass, 35.45, is closer to 35 than 37. Looking at the four choices, we can eliminate choice D because it says that there is a greater abundance of 37 than 35. So let's eliminate choice D. Now we can do the math. And the way we do the math is we multiply the mass number by the percent abundance as a decimal. So 35 times 0.86 plus 37 times 0.14. Now that gives us 35.28. That's not close enough to the average atomic mass. It should be closer to around 35.5. Let's move on to choice B. 35 times 0.76 plus 37 times 0.24. That's looking pretty good. Let's move on to part C, choice C, and we get 35 times 0.56 plus 37 times 0.44, and that's 35.88. That's not close enough. So the best choice, based on the math, is choice B, which gives us an average atomic mass of approximately 35.5, which is close enough to what it says on the periodic table. All right, moving on to question 33. Based on the information in the table above, which of the following methods is the correct way to calculate the average atomic mass of rubidium? Well, we just saw in the previous question how to do this. You multiply the mass number by the percent abundance as a decimal. So it's going to be 85 in this case for rubidium times the abundance as a decimal, 0.72, plus 87, the other mass number, times its percent abundance as a decimal, 0.28. And sure enough, we get a value of 85.56, which is pretty close to 85.47. In other words, it's close to the average atomic mass that we see on the periodic table. So the correct setup for this calculation is choice B. All right, now 34 is not a multiple choice question, but you have to do that same type of calculation that we talked about in question 33 as well as in question 32. So here, set up the calculation by multiplying the mass number of each isotope by the natural abundance as a decimal. So we'll start with 54 times 0.058 plus 56 times 0.918 plus 57 times 0.020. And then watch out for that last one because it's actually 0.3%, which means when you move the decimal over 2 spaces to the left by dividing by 100, that number, 0.3%, is actually 0.003. So watch out for that. When you do all of this math, you get 55.854. Now, part B, write the symbol for the element whose isotope data is shown in the table above. When we look on the periodic table to see an element that has an average atomic mass that's pretty close to 55.85, correct answer is going to be iron, which has the symbol Fe. So in question 34, we knew the natural abundance of each of these 4 isotopes of iron. In question 35, there are 2 isotopes of antimony, which has the elemental symbol Sb, but we do not know the natural abundance of each isotope. So we're going to use algebra to solve for the natural abundance of each isotope. So here's what we can do. Let's go ahead and let X equal the abundance of antimony 121, and that would be as a decimal. So for example, if it was 25%, it would be expressed as 0.25. And since there are only 2 isotopes, and they would add up to equal 100%, or in this case, they would add up to equal 1 in the form of a decimal, if X is the abundance of one isotope, then 1 minus X would be the abundance of the other isotope. And we know the identity of the element, so therefore we know the average atomic mass, which we get off the periodic table, 121.76. So here's how we do this in terms of X. 121 times the abundance of that isotope, which would be X, plus 123 times the abundance of the other isotope, which is 1 minus X. And we set that equal to the average atomic mass, which we can pull off of the periodic table for this element, for antimony. Now we're going to do the algebra. 121X plus 123 minus 123X equals the total, 121.76. Now on the left side of the equation, when we combine like terms, we're going to have negative 2x. And when we subtract 123 from both sides of the equation, we get negative 1.24. So let's divide both sides by negative 2. And our answer, as we solve for x, is x equals 0.62. Remember, that is the percent abundance as a decimal. So it's 62% for antimony 121, and then 38% for antimony 123. All right, moving on to the next question, question 35. We have a large table with 9 different rows, and we have to fill in the missing information into this table. So we'll start with the very first row here, which is Pa, that's protactinium 231. So the mass number is 231. Let's take a look at protactinium on the periodic table. So the elemental symbol is Pa, and its atomic number is 91. So it has 91 protons. Remember that charge equals protons minus electrons, but this symbol does not have a charge, so therefore the overall charge is 0. We have 91 protons and 91 electrons. Remember that the mass number is protons plus neutrons, so we already know the mass number is 231. The number of protons is 91, so 91 plus what number would equal 231, and the answer is 140. Essentially, we did 231 minus 91 to get the number of neutrons. All right, in our next row of the table, this is selenium. It has a mass number of 79. When we go look at selenium on the periodic table, it has atomic number 34, so it's 34 protons. Charge equals protons minus electrons. And unlike the last example, this is not a neutral atom, this is a -2 ion. So if the charge is -2, that means it gained 2 electrons. So 34 protons and 36 electrons would give you a charge of -2. The mass number is the sum of the protons and the neutrons. So we know we have 34 protons, so 34 plus what number is 79, and the answer is 45. So we essentially did 79 minus 34 to get the number of neutrons. In the next row of the table, we have an isotope of barium, and it has a charge of 2+. So the mass of this particular isotope is 137. Let's take a look at barium on the periodic table. Barium has atomic number 56, so 56 protons. If it has a +2 charge, that means it lost 2 electrons. So 56 protons and 54 electrons would give us a charge of +2. The mass is 137, which is the sum of the protons and neutrons. So 137 equals 56 protons plus what number? And again, that would be 81 neutrons, because 56 plus 81 is 137. All right, now our next example, we don't have the elemental symbol. So to figure this out, let's take a look at the number of protons. So which element has atomic number 64? And it turns out to be gadolinium, which has the elemental symbol Gd, and the mass number that we're going to use from the table is 157. Now, if this has a charge, then there'd be a different number of electrons. But since we have the same number of electrons, then this is a neutral atom. There is no charge. The charge is 0. To get the neutrons, it's mass number minus protons. So 157 minus 64 is 93. 64 plus 93 is 157. In our next example, we have 39 protons. So we're looking for an element with atomic number 39, and that happens to be yttrium, which is the atomic symbol Y. And the mass number is 89. So we'll start with the symbol 89 and then the elemental symbol Y. Now, if this were a neutral atom like it was in the last example, then there would be no charge. But this is not a neutral atom because the number of electrons is different than the number of protons. In fact, looks like the atom lost 3 electrons, so therefore it should have a charge of positive 3. So 39 minus 36 equals positive 3. Let's put a little 3 plus as a superscript in the upper right corner of that symbol like that. Now to get the number of neutrons, it will be mass number, so 89, minus atomic number, 39. That's a difference of 50. So 39 plus 50 is 89. Protons plus neutrons equals mass number. Our next example has atomic number 35. So on the periodic table, atomic number 35 is bromine with the symbol Br. We know the mass number is 80 according to the information in the table. So we can write Br with a mass of 80. Does this have a charge? And the answer is yes, because the electrons are different than the number of protons. 36 is larger than 35. It looks like this atom gained 1 electron. So protons minus electrons equals charge. 35 minus 36 is negative 1. Let's put a little minus sign in the upper right corner as a superscript to show the charge on this ion. And then neutrons would be protons and neutrons added together. We know the protons are 35. We know the mass is 80. So 80 minus 35 is 45. 45 neutrons. 35 protons plus 45 neutrons equals a mass number of 80. Now in these last 3 examples of the table, we don't know the mass number, but we do know everything in terms of protons, electrons, and neutrons. So let's start off with the elemental symbol. Atomic number 15, so 15 protons, would be phosphorus, which is capital P. We know that the mass number is the protons plus the neutrons. So since 15 plus 17 is 32, then this particular isotope of phosphorus has a mass number of 32. So we can write the mass number in the table. We can write capital P for phosphorus and then a little 32 for the mass number. This isotope of phosphorus is not the most common isotope since the average atomic mass is around 31, but that's okay. We use the information in the table even if that mass number doesn't match the average atomic mass on the periodic table. All right, does this have a charge? Let's take a look at the electrons. Yes, it has a charge because 18 is different than 15. It looks like this atom gained 3 electrons. So 15 minus 18 is negative 3. This has a charge of 3 minus, which we can put in the upper right corner as a superscript. All right, moving on to our next example. 45 is atomic number of rhodium, which has the symbol Rh. Now we know the symbol, let's get the mass number by adding protons plus neutrons. So 45 plus 58 is 103. So the mass number is 103. We can write the symbol rhodium 103, and this does not have a charge because it's 45 protons and 45 electrons. Therefore, the charge would be 0. So there is no charge to write in the upper right corner for this particular example. The final row of the table, it's 55. Let's go find atomic number 55, which is cesium, so Cs. The mass number would be 55 plus 78, and that works out to be 133. So the mass number, protons plus neutrons, 133. Let's write the symbol, cesium 133. Does it have a charge? Yes, because electrons are different than protons. 55 minus 54. It looks like it lost 1 electron, so it has a positive 1 charge. So let's put a little superscript above the CS on the right corner there with a plus sign, indicating that the charge on the ion is +1. All right, well, those are the answers to that particular table, and now we can move on to question 37. Question 37 says write balanced nuclear decay equations for each of the following. Part A, Seaborgium-266 undergoes alpha decay. Part B, chromium-55 undergoes beta decay. So to remind you about alpha decay, here's an example where uranium-238 undergoes alpha decay and produces thorium-234. So in an alpha decay reaction, the mass number of the unstable isotope, also known as a radioisotope, decreases by 4 units. In this example, it went from 238 to 234. And the atomic number decreases by 2 units. In this example, it went from 92 to 90. The symbol for an alpha particle would be 4 on the top, 2 on the bottom, then we can use the Greek letter alpha. So, Seaborgium-266, let's find the atomic number of Sg on the periodic table. The atomic number is 106, so it's going to be 266 on the top, 106 on the bottom, and then the symbol Sg. On the right side of the arrow, we have an alpha particle, so 4 over 2, alpha, and then plus question mark. The mass number of this element that is going to be the new element produced in this alpha decay equation, the mass number is 262 because it's decreased by 4 units. So 266 minus 4, 262. The atomic number has gone down by 2 units, so 106 minus 2 is 104. And the elemental symbol would be for atomic number 104. That happens to be rutherfordium, so the symbol for rutherfordium is Rf. Now moving on to part B, chromium-55 undergoes beta decay. So to remind you about beta decay, what happens in beta decay in this example is carbon-14 undergoes beta decay to produce nitrogen-14. In beta decay, the mass number of the radioisotope is unchanged, and the atomic number increases by 1 unit. So what happens is that one of the neutrons turns into a proton, the mass number stays the same, and the atomic number increases by 1 unit. So chromium, let's go find chromium on the periodic table. It has atomic number 24. So it's going to be 55 on top, 24 on the bottom, and the symbol is Cr. Then we're going to show a beta particle, which is 0 over -1 on the right side of the equation, and then we have a question mark. The new element should have a mass of 55, and the atomic number is going to go up by 1, so it's going to be 25. Let's go find the symbol for the element that has atomic number 25. It should be right next to chromium on the periodic table, and that's manganese, elemental symbol Mn. So now question 37 is complete. Let's take a look at question 38. Question 38 says the half-life of radium-233 is 30 seconds. If you have 40 grams of radium-233 right now, how many grams of radium-233 will remain after 120 seconds have passed? Show your calculations below and include units in your answer. So we have 40 grams of radium-233 right now. The total time is 120 seconds. The half-life is 30 seconds. So if we take the total time divided by the half-life, that's equal to 4 half-life periods. Now let's divide 40 grams by 2. That's 1 half-life period. Let's divide 20 grams by 2. That's another half-life period. Let's divide 10 grams by 2. Another half-life period. Then we have 1 more half-life period, and we get down to 2.5 grams. So our final answer, how much of this radium-233 will remain? The answer is 2.5 grams. In our next question, which is question 39, it says the half-life of sodium-24 is 15 hours. If you have a sample of sodium-24 that weighs 2 grams right now, how many grams of sodium-24 was present in the sample 45 hours ago? So it weighs 2 grams right now, but we're going to have to go back in time and figure out how much it weighed 45 hours ago. So 15 hours is one half-life. 45 hours is the total time. 45 divided by 15 is 3. That's 3 half-life periods. But we're going backwards in time, which means we're multiplying by 2. So one half-life period ago, it was 4 grams. Another half-life period ago in the past, it would be 8 grams. And if we go backwards one more half-life period, that would be 16 grams. So how many grams of sodium-24 was present in the sample 45 hours ago? The answer is 16 grams. All right, let's move on to question 40. The half-life of manganese-52 is 6 days. How long will it take for a sample of manganese-52 to decay from a mass of 240 grams to a mass of 7.5 grams? Well, let's start with 240. Let's divide by 2, so now we have 120. Divide by 2, now we have 60. Divide by 2, now we have 30. Divide by 2, now we have 15. And then one more, divide by 2, now we have 7.5. Let's count the number of half-life periods. So what I see is a total of 5 arrows. Each arrow is a half-life period, so we have 5 half-life periods. The half-life of manganese-52 is 6 days. So if we have 5 of these half-life periods, then 5 times 6 days will equal how long it will take, and that is 30 days. So that's going to be our final answer in this question, 30 days. And now let's move on to number 41. A sample of fluorine-18 decays from 51.2 grams to 0.8 grams over a period of 660 minutes. What is the half-life of fluorine-18? So we'll start with 51.2 grams, and then we'll keep dividing by 2 until we get to 0.8 grams. So 51.2, half of that is 25.6. Then we divide by 2 again, and we get 12.8. We divide by 2 again, and we get 6.4. Divide by 2 again, and we get 3.2. Divide by 2, 1.6, and then one more half-life period. 1.6 divided by 2 is 0.8. Now let's count the number of half-life periods it took to get from the beginning to the end. So I see a total of 6 arrows, which is 6 half-life periods. We don't know the half-life of fluorine-18, but we do know that the total time is 660 minutes. If we take the total time divided by the number of half-life periods, in this case 660 divided by 6, the half-life of fluorine-18 is going to be 110 minutes. So that is our answer. Now, question 41 was the last question on the practice test. So this is the end of the atomic structure and nuclear chemistry practice test video. I hope that you found these answers and explanations helpful. Thanks for watching, and good luck studying for your test.